What if we're not alone in the universe, not just in the sense of microbial life or distant planets, but in the existence of civilizations so advanced, their engineering feats reshape entire star systems? Picture a structure so colossal, so unimaginably powerful, it captures the energy of an entire star. This isn't science fiction, it's a Dyson Sphere, a hypothetical megastructure that could be the ultimate signature of a civilization far beyond our own. The idea was first proposed by physicist Freeman Dyson in the 1960s, but today, it's more than just a thought experiment. It's a beacon in our search for intelligent life, a clue hidden in the cosmos waiting to be discovered. Think about the scale for a moment. A civilization capable of building a Dyson Sphere wouldn't just be slightly ahead of us, they'd be millions, maybe billions of years more advanced. They'd have mastered energy on a scale we can barely comprehend, harnessing the raw power of their sun to fuel technologies beyond our wildest dreams. And here's the thrilling part, we might already have the tools to find them. Astronomers are scanning the skies for strange, unnatural dips in starlight patterns that don't match any known cosmic phenomenon. Could these anomalies be the fingerprints of something built? This video is a journey into that possibility. We'll explore how Dyson Spheres work, why they're such a compelling target in the hunt for extraterrestrial intelligence, and what it would mean if we actually found one. Along the way, we'll dive into the mind-bending physics behind these megastructures, the ongoing searches hunting for them right now, and the profound implications for humanity's place in the universe. Because if we're right, if even one of these cosmic giants is out there, it changes everything, so buckle up. We're about to take a trip to the far edges of science, engineering, and imagination, where the line between today's theories and tomorrow's discoveries blurs into something extraordinary. The question has haunted scientists for decades. If the universe is so vast and so old, why haven't we found any signs of intelligent life out there? This is the Fermi Paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" On paper, the numbers seem overwhelming. With billions of galaxies, each packed with billions of stars, the odds of Earth being the only planet to foster life seem vanishingly small. So why does the cosmos appear so silent? One possibility is that advanced civilizations don't announce themselves in ways we'd expect. Radio signals might be too primitive, like trying to spot a candle in a hurricane. Instead, a species with technology far beyond ours might leave subtler traces, cosmic construction projects on an unimaginable scale. That's where Dyson Spheres come in. If a civilization reaches a point where it needs staggering amounts of energy, capturing the full output of a star would be the ultimate solution. But here's the catch, a Dyson Sphere wouldn't just hide a star's light, it would irradiate that energy as heat glowing in infrared. That's a signature we can detect even across interstellar distances. Another angle to the Fermi Paradox is timing. Civilizations might rise and fall in cosmic blinks, their relics fading before we ever notice. Or perhaps they're avoiding us deliberately, a theory called the zoo hypothesis. But if Dyson Spheres exist, they'd be long-term projects, the work of societies that have mastered their survival for millions of years. Finding even one would shatter the silence, proving that intelligence isn't just possible, it can endure. So the search for these megastructures isn't just about curiosity. It's a test of our deepest cosmic loneliness. If we discover a Dyson Sphere, it means we're not alone, and that the universe might hum with civilizations too advanced for us to yet comprehend. But if we find nothing, the paradox only deepens. Are we early? Are we rare? Or is there something about intelligence that inevitably leads to its own undoing? These aren't just scientific questions, they're existential ones, and the hunt for Dyson Spheres might be our best shot at answers. At its core, a Dyson Sphere is a concept so audacious, it bends our understanding of engineering and energy. Imagine a civilization so advanced that building planets or moons isn't enough. They need to harness the power of an entire star. That's the essence of a Dyson sphere, a colossal structure, whether a solid shell or a swirling swarm of orbiting collectors, designed to capture every photon of sunlight and convert it into usable energy. Think of it as the ultimate power plant, one that doesn't just tap into a fraction of a star's output, but all of it. Freeman Dyson, the visionary physicist who first proposed the idea in 1960, didn't actually imagine a rigid, solid sphere. His original concept was far more practical, a Dyson swarm of millions or even billions of independent solar collectors, satellites, and habitats orbiting a star in tight formation. This swarm would gradually grow over time, soaking up sunlight like leaves on a tree, until it formed a loose but comprehensive net around the star. Pop culture often depicts Dyson spheres as seamless, artificial worlds. Think a giant, glowing ball enclosing a sun, but the reality would likely be messier, more dynamic, and far more fascinating. Why would any civilization attempt such a feat? The answer lies in energy demands. Humanity's energy consumption doubles roughly every few decades. Extrapolate that trend over thousands or millions of years, and even the most efficient fusion reactors or antimatter generators might not suffice. A star, by contrast, emits enough energy in a single second to power our current civilization for hundreds of thousands of years. A Dyson sphere isn't just about luxury. It's about survival, expansion, and unlocking possibilities we can't yet fathom. Advanced societies might use this energy for computational megaprojects, interstellar travel, or even reshaping matter itself. The beauty of Dyson's idea is that it's rooted in physics, not fantasy. We already have the mathematical frameworks to understand how such structures might behave, how they'd balance gravitational forces, manage heat dissipation, or even navigate the delicate dance of orbital mechanics. And while we're centuries or more away from building one ourselves, the theoretical groundwork makes Dyson spheres a perfect candidate in the search for extraterrestrial intelligence. After all, if another civilization has already constructed one, the signs would be written across the cosmos in infrared glow and unnatural shadows. Dyson's original paper was just 2 pages long, but its implications stretch across light years. It challenges us to think not just about what's possible with today's technology, but what might be inevitable for any civilization determined to thrive among the stars. The concept has evolved from a speculative footnote to a cornerstone of astrobiology, a yardstick for measuring how advanced a society might truly be. And whether we ever find one or not, the mere idea expands our vision of what's out there and what we might someday become. Freeman Dyson's original vision of a solar-collecting megastructure wasn't a single monolithic shell, it was something far more adaptable. When we talk about Dyson spheres today, we're actually dealing with a spectrum of designs, each with its own staggering possibilities and impracticalities. The simplest form is the Dyson swarm, the closest to Dyson's initial concept. Picture trillions of solar collectors, mirrors, or habitats orbiting a star in a dense, coordinated dance. Unlike a solid sphere, a swarm avoids the impossible stresses of a single rigid structure while still capturing vast amounts of energy. Individual components could be added incrementally, making it the most achievable version for an emerging spacefaring civilization. But don't mistake simplest for easy. Even a swarm requires mastering asteroid mining, self-replicating robotics, and orbital mechanics on an unprecedented scale. Then there's the Dyson bubble, a more exotic variation where stationary solar sails balance against a star's radiation pressure, holding position without orbiting. Think of it like a vast fleet of hot air balloons, each sail hovering in place by riding the very sunlight it's collecting. This design sidesteps the collision risks of orbiting swarm elements, but introduces new headaches, like how to maintain stability across millions of fragile collectors without gravity or orbits keeping them in line. The bubble is elegant in theory, but would demand materials stronger than anything we know, possibly relying on hypothetical supermaterials like carbon nanotubes or graphene sheets kilometers wide. At the far end of the spectrum lies the Dyson shell, the classic sci-fi image of a solid sphere encasing a star. It's also the most unrealistic. The engineering nightmares pile up fast. A rigid shell would experience crushing gravitational forces, requiring materials with impossible tensile strength. Even if built, any slight asymmetry could send the entire structure crashing into the star. Then there's the issue of heat. Trapping all that stellar energy would turn the sphere's interior into an oven, requiring unimaginable cooling systems. Some theorists suggest a partial shell with massive open areas might work, but at that point you're reinventing the swarm with extra steps. Why does this taxonomy matter? Because each design leaves different cosmic footprints. A mature Dyson swarm might dim a star unevenly as its components drift in and out of alignment, creating a flickering effect detectable by telescopes. A bubble could appear as a strange, shimmering haze around a star, while a failed shell might manifest as an absurdly hot debris ring. These distinctions help astronomers know what to look for, because if we're scanning the galaxy for alien megaprojects, we need to recognize all their possible forms. The takeaway isn't just about hypothetical alien tech, it's a mirror for our own future. The swarm model suggests a path forward where humanity could start small, building individual orbital habitats or solar mirrors that gradually scale up over centuries. It's less about sudden leaps than steady, exponential growth, a lesson in how civilizations might expand without magical technology. Meanwhile, the implausibility of solid shells reminds us that even advanced beings must obey physics. No matter how brilliant a species becomes, starlight won't bend to their will without overcoming brutal engineering constraints. That duality between incremental progress and hard limits might define not just how we search for aliens, but how we shape our own destiny among the stars. Why would any species, no matter how brilliant, commit the astronomical effort required to reshape a star? The answer lies in the relentless hunger for energy, a force that drives civilizations from fire to fusion. Consider humanity's own trajectory. Our global energy consumption has skyrocketed over the past century, doubling roughly every 32 years. If that trend continues even at a fraction of the pace, we'd outstrip Earth's resources in centuries, not millennia. Now imagine a society a million years ahead of us, their ambitions stretching across star systems. For them, a Dyson sphere wouldn't be a luxury, it'd be a necessity. One compelling motivation is sheer survival. As a civilization expands, so does its need for stable, scalable energy. Stars are the universe's ultimate batteries. Our sun alone emits 380 sextillion watts of power every second. Capturing even a fraction of that could sustain habitats, terraforming projects, or ark ships carrying populations away from dying stars. A Kardashev Type II civilization, defined by its ability to harness all the energy of its home star, wouldn't just thrive, it'd become unstoppable. Picture a species so advanced they treat stellar engines like we treat power plants, not as marvels but as infrastructure. But energy isn't just about survival, it's about transcendence. Some theorists propose that advanced civilizations might build Dyson spheres to fuel computational megaprojects. Imagine a single Matryoshka brain, a planet-sized supercomputer wrapped around a star, dedicating its entire output to running simulations or solving physics problems beyond our comprehension. Or consider the possibility of art on a cosmic scale. A Dyson sphere could be the ultimate canvas, its surface or swarm components rearranged to broadcast patterns visible across galaxies. Humanity's own energy cravings hint at this future. Bitcoin mining alone consumes more electricity annually than some small nations. Mega data centers guzzle power to fuel AI and cloud storage. These are embryonic signs of a species pushing against its planetary limits. The leap from burning fossil fuels to dismantling planets for construction materials might seem absurd, but so would a smartphone to a medieval farmer. Yet there's a darker angle. What if Dyson spheres aren't just monuments to ingenuity, but warnings? A civilization that exhausts its local resources might have no choice but to cannibalize its solar system, leaving behind a star cloaked in metal and silicon. Could these structures be tombstones as much as triumphs? The question forces us to confront our own trajectory. Will we learn to balance growth with sustainability? Or will we too one day become desperados of the cosmos, stripping stars bare to keep the lights on? The motivations behind a Dyson sphere reveal as much about a civilization's values as its technology. Whether built for survival, knowledge, or sheer ambition, these megastructures would stand as testaments to life's audacity, proof that intelligence, given enough time, can reshape the universe itself. And that raises another chilling thought. If such civilizations exist, why haven't they contacted us? Perhaps the answer lies not in the stars, but in what it takes to build around them. The Kardashev Scale offers a humbling perspective on where humanity stands in the cosmic pecking order, and just how far we'd need to go to join the league of civilizations capable of building Dyson spheres. Proposed by Soviet astronomer Nikolai Kardashev in 1964, this framework classifies societies based on their energy mastery. A Type 1 civilization harnesses all available power on its home planet, every gust of wind, every ray of sunlight, every drop of oil. We're not there yet. Currently, humanity hovers around Type 0.7, still tethered to fossil fuels and barely scratching the surface of planetary-scale renewables. Reaching Type 2 is where the game changes dramatically. This is the realm of Dyson Spheres civilizations that don't just use their world's energy but their stars. Imagine controlling the entire output of our sun, channeling its energy into interstellar travel, megacities floating in space, or computational projects dwarfing all human knowledge combined. That's the power threshold a Type 2 society operates on. And while it might sound like fantasy, the physics checks out. The energy difference between Type 1 and Type 2 isn't incremental, it's exponential, like comparing a campfire to a supernova. Then there's Type 3, where things get truly mind-bending. These civilizations have graduated from single stars to controlling the energy of entire galaxies, possibly through networks of Dyson spheres or even more exotic megastructures. The energy scales here are so vast they border on incomprehensible. A Type 3 society might re-engineer stars, manipulate dark matter, or traverse billions of light years as casually as we cross oceans. This scale isn't just about raw power, it's about survival timelines. Most species probably never make it past Type 1. Climate catastrophes, wars, or resource collapses could halt progress long before a civilization reaches for the stars. That's why Dyson spheres are such tantalizing targets in the search for extraterrestrial intelligence. Finding one wouldn't just prove we're not alone, it'd reveal a society that overcame the existential traps we're still grappling with. They'd be the elders of the cosmos, holding blueprints for longevity we can only dream of. For humanity, the path forward is both daunting and electrifying. To reach Type 1, we'd need to perfect fusion, master global energy grids, and likely erase national borders in favor of planetary cooperation. Type 2 would demand dismantling Mercury for construction materials and building robotic fleets capable of engineering solar systems. Each step seems impossible until you realize every civilization starts where we are now limited, fragile, but teeming with potential. The Kardashev Scale isn't a prophecy. It's a mirror forcing us to ask, will we be among the species that transcend, or will we fade into cosmic silence, leaving the stars to others? The answer hinges not just on technology, but on whether we can grow up as a species before our energy appetite outstrips our wisdom. Detecting something as vast as a Dyson sphere might seem impossible after all. How do you spot a structure that could dwarf entire solar systems? The answer lies in the laws of physics themselves. Every action leaves a trace, and a civilization capable of encasing a star would leave one of the most glaring cosmic fingerprints imaginable: heat. Here's why. When a star's light is captured by a Dyson sphere or swarm, that energy doesn't just vanish. It's absorbed, used, and ultimately re-emitted as infrared radiation, the same type of warmth you feel from a radiator or sunlight on your skin. That means even the most advanced megastructure couldn't hide its waste heat. It's like trying to hide a bonfire in a snowstorm. The universe always keeps receipts. This insight has shaped one of the most promising strategies in the hunt for alien megastructures. Since the 1960s, astronomers have scanned the cosmos for stars that seem oddly dim in visible light but blazing in infrared, a mismatch that defies natural explanations. Projects like Glimpsing Heat from Alien Technologies, or GHT for short, have spearheaded this effort, sifting through data from telescopes like NASA WISE, which maps the sky in infrared wavelength. The idea isn't just to find any warm object, but to pinpoint stars whose heat signatures look engineered. Imagine a sun that emits only half the visible light it should, yet glows unnaturally bright in thermal radiation. That's the kind of anomaly that could signal a Dyson sphere in progress. Of course, nature loves playing tricks. Dust clouds, newborn stars, and even certain types of dying stars can mimic these infrared excesses. That's why researchers don't just look for heat, they hunt for specific patterns. A natural dust ring might glow unevenly, while a Dyson swarm could radiate heat more uniformly, like a halo. Some scientists even search for stars that flicker irregularly, as if massive orbiting structures are passing in front of them. The key is to rule out every possible astrophysical explanation before whispering the thrilling possibility: this might not be natural. One of the most famous candidates emerged in 2015 when astronomers noticed a star called KIC 8462852, nicknamed Tabby star, dimming by up to 20% in erratic bursts. The dips didn't match any known planet or dust formation. For a while, theories swirled about a partial Dyson swarm under construction. Further study suggested more mundane causes, like clouds of disintegrating comets, but the mystery highlighted how detection works. It's a process of elimination where the strangest outliers become prime targets. The search has grown even more sophisticated. Modern algorithms comb through millions of stars in archival data, flagging anomalies humans might miss. Other teams explore secondary clues, like the absence of certain elements in a star's light materials that might have been mined away for construction. And while no definitive Dyson sphere has been found yet, the pursuit itself is reshaping astronomy. It's teaching us to look at the universe not just as a collection of natural wonders, but as a potential catalog of engineering projects, some of which might belong to civilizations we've yet to meet. What makes this hunt so profound isn't just the potential discovery. It's the realization that even the grandest alien artifacts would still obey the laws of thermodynamics. No matter how advanced a species becomes, energy can neither be created nor destroyed, only transformed. That means every Dyson sphere, no matter how vast, would leave a trail of warmth across the cosmos. And that's our best hope, that somewhere in the sea of data we'll spot the glow of a civilization that learned to bottle starlight. Until then, we keep watching the skies, not just for signals, but for the heat signatures of ambition itself. In 2015, astronomers stumbled upon a star so strange, it reignited one of the most tantalizing questions in science. Could this be evidence of alien engineering? Known as KIC 8462852, or Tabby star, after the scientist who led its discovery, Tabitha Boyajian, this unassuming flicker of light in the constellation Cygnus quickly became the most debated star in the galaxy. While most stars dim in predictable, rhythmic patterns caused by orbiting planets, Tabby's star plunged in brightness by up to 20% in chaotic, uneven dips, like someone was flicking a cosmic dimmer switch at random. The strangest part, some of these dips lasted for days, others for weeks, with no clear pattern. When natural explanations fell short, the boldest hypothesis emerged. What if we were seeing a partially built Dyson swarm? Imagine vast solar collectors or habitats orbiting the star in dense clusters, their irregular arrangements casting erratic shadows as they drifted. The idea wasn't entirely far-fetched. A civilization transitioning to Type 2 status might construct megastructures piecemeal, creating exactly the kind of erratic dimming Tabby's star exhibited. Even the star's slight infrared excess, a faint warmth beyond its expected heat, fit the profile of waste energy radiating from alien technology. For a brief, electrifying moment, the scientific world held its breath. Of course, extraordinary claims demand extraordinary evidence. Critics quickly pointed to less exotic possibilities. Maybe the star was shrouded in clouds of dust from colliding planets or swarms of comets. Others proposed that Tabby's star was simply a rare type of variable star with poorly understood activity. Follow-up observations revealed dust was indeed a likely culprit. Microscopic particles absorbing and scattering light could explain both the dimming and the infrared glow. But the dust itself raised new questions. Why was it so uneven? Why didn't it behave like dust around other stars? The mystery deepened even as the Dyson Sphere hypothesis faded. What makes Tabby's star so compelling isn't just the unresolved puzzle, it's how it transformed the search for alien megastructures. Before this discovery, most astronomers considered Dyson spheres a fringe topic, the stuff of thought experiments. But here was a real star in real data, defying every natural explanation. Suddenly, the hunt for cosmic anomalies became mainstream science. Teams began revisiting old telescope archives, searching for other stars with similar oddities. New monitoring projects sprang up, watching hundreds of thousands of stars for the slightest flicker that might betray alien construction. The legacy of Tabby's star isn't a confirmed Dyson sphere, it's the blueprint for how to look for one. It taught us that the signatures of advanced civilizations might not be radio signals or flashing lights, but subtle, stubborn irregularities in the humdrum data of the cosmos. And it proved that even when nature offers mundane explanations, the outliers, the stars that refuse to behave, are still our best leads in a universe that may be hiding engineers far greater than ourselves. So while dust may have dimmed the lights on this particular mystery, the search is brighter than ever. The next Tabby star could be hiding in plain sight, waiting for someone to notice its unnatural wink. Tabby's star isn't the only cosmic oddball that's made scientists wonder if we're glimpsing alien megastructures. Take Epic 204278916, a young star in the Scorpius constellation that behaves like nothing else in the known universe. In 2016, astronomers watched in disbelief as this star's light dropped by a staggering 65%, not once, but multiple times in irregular, jagged dips. For comparison, even a Jupiter-sized planet passing in front of a star would only block about 1% of its light. Something colossal was obscuring Epic 204278916, and it wasn't playing by nature's rules. At first, researchers scrambled for conventional explanations. Could it be a massive ringed planet like Saturn on steroids? Unlikely. The dips were too deep and too chaotic. Maybe a swarm of comets. The scale was implausible. You'd need millions of them, packed impossibly tight. A warped protoplanetary disk. The star's age fit, but the light patterns didn't. With each hypothesis falling short, the door cracked open for wilder possibilities. Could this be a Dyson swarm under construction, a messy, half-finished cage of solar collectors throwing unpredictable shadows across the cosmos? Then there's VVVWIT-07, a giant star near the Milky Way's center that dimmed by a staggering 80% over several years before slowly brightening again. Whatever blocked it wasn't just big, it was opaque, like a solid curtain drawn across the star. Natural explanations, a rogue planet trailing a titanic dust cloud, might fit, but the numbers are strained. An artificial megastructure, even one partially completed, would explain the star's dramatic vanishing act with eerie elegance. What makes these candidates so tantalizing isn't just their strangeness, it's their inconsistency. Natural phenomena tend to follow patterns. Planets orbit predictably, dust clouds disperse evenly, but EPIC 204278916 and VVVWIT07 flicker like faulty light bulbs, defying every model astronomers throw at them. That unpredictability is what keeps the Dyson Sphere hypothesis alive, even as skeptics rightfully demand more evidence. After all, the universe is under no obligation to make sense to us, especially not on human timescales. But here's the catch: weirdness alone isn't proof. For every potential Dyson Sphere candidate, there's a team of scientists digging for mundane answers. EPIC 204278916 might be surrounded by a warped disk of planet-forming debris, tilted at just the right angle to create those bizarre shadows. VVVWIT07 could be eclipsed by a previously unseen type of stellar companion, cloaked in dust. The real lesson isn't that these stars are definitely alien engineering, it's that they're mysteries, and mysteries are the compass points guiding us toward new physics, whether natural or otherwise. That's the tightrope walk of astrobiology. Get too excited and you risk seeing aliens in every shadow. Stay too cautious and you might miss the signature of a civilization shouting its presence across the light years. So for now, these stars remain cosmic Rorschach tests, blank slates where we project our hopes, our doubts, and our burning curiosity about whether we're truly alone. The hunt continues, not just for answers, but for better questions. And with every oddball star we catalogue, the universe feels a little stranger, a little richer, and infinitely more worth exploring. Building a Dyson Sphere isn't just an engineering challenge, it's a confrontation with the brutal limits of physics itself. Let's start with the most obvious hurdle: materials. To encase a star, you'd need more matter than exists in all the planets of a solar system combined. Take our Sun. Constructing a solid shell around it would require ripping apart every planet, moon, and asteroid out to Jupiter, grinding them into raw materials, and somehow forging them into a structure with the tensile strength of a fantasy. Even a Dyson swarm, the more plausible alternative, would demand strip mining Mercury or Venus entirely, converting whole worlds into trillions of solar satellites. The scale is so vast it redefines the word megaproject. Then there's the stability nightmare. A solid Dyson Sphere would experience unimaginable gravitational stresses. Any imbalance would send it careening into the star. Picture balancing a teacup on a needle while earthquakes shake the table. Even a swarm presents orbital chaos on an epic scale. Maintaining billions of collectors in precise formation without collisions would require constant, flawless adjustments. One miscalculation could trigger a cascade of destruction, like cosmic dominoes smashing into each other at thousands of kilometers per second. Heat management is another deal-breaker. Capturing a star's energy doesn't make it disappear. It turns the megastructure into a searing radiator. Without a way to dissipate that heat, the interior would cook itself into molten slag. Earth's entire surface receives just a fraction of the Sun's output, and we already struggle with global warming. Now imagine handling all of it. Advanced civilizations might use this heat as an energy source or radiate it into space, but the engineering would dwarf anything humanity has ever attempted. Time is the silent killer of such ambitions. Even with self-replicating robots and exponential construction rates, building a Dyson Sphere could take millennia. Civilizations rise and fall in shorter spans. Political upheavals, cultural shifts, or cosmic disasters could derail progress over such timescales. It's like planning a skyscraper where each brick takes a generation to lay. The builders who start it would never see it finished. The project would need a society stable enough to endure wars, resource shortages, and existential boredom, all while staying committed to a vision spanning longer than recorded human history. And yet, the most terrifying challenge might be the one we least expect: motivation. Would any civilization want to build one? The energy demands are obvious, but the costs, ecological, ethical, and existential, are staggering. Dismantling planets means destroying every ecosystem they harbor. Committing to a Dyson Sphere is a declaration that growth outweighs preservation, that energy hunger justifies cosmic-scale strip mining. It forces a question: is this the destiny of all advanced life, or just the path of those who value power over balance? The obstacles aren't just technical. They're philosophical, forcing us to ask what kind of civilization we'd become to reach for the stars, and what we might destroy to get there. Could humanity ever construct something as colossal as a Dyson Sphere? The question straddles the line between ambition and absurdity. But let's break it down piece by piece. Right now, we're infants in the cosmic construction business. Our greatest off-world achievement is the International Space Station, a tin can compared to the megastructures we're imagining, yet the seeds of potential are there. Robotics and AI are advancing at breakneck speed. Swarms of autonomous drones already assemble structures on Earth. Scaled up, they could mine asteroids or fabricate solar collectors in orbit. Nanotechnology hints at self-replicating machines that could multiply exponentially, turning raw asteroid material into trillions of energy-harvesting satellites. These aren't sci-fi fantasies, they're extensions of existing research, just waiting for time and iteration. Timelines are the great unknown. Optimists like futurist Ray Kurzweil suggest we might reach Kardashev Type 1 status planetary energy mastery within a century or two. From there, a Dyson swarm could follow in another 1,000 years, built incrementally by self-replicating robots. Pessimists counter that civilizational collapse, climate disasters, wars, or resource depletion could derail us long before. The truth likely lies in between. Even with perfect technology, the sociopolitical hurdles are staggering. Coordinating a multi-millennium project demands stability beyond anything humanity has achieved. Ancient Egypt's pyramids took decades. A Dyson Sphere would require generations of workers, or more likely, armies of machines to stay on task. Ethics loom just as large. To build a Dyson swarm, we'd need to dismantle planets. Mercury, rich in metals and close to the sun, would be prime real estate for mining. But what right do we have to erase a world, even a barren one? Ecologists warn of unintended consequences. Altering a planet's mass could destabilize orbits across the solar system. And who decides which nations or corporations control the star's energy output? The potential for conflict is astronomical, pun intended. Yet, the most profound obstacle might be philosophical. A Dyson Sphere represents exponential growth in a universe of finite resources, a mindset that could doom us before we even start. Perhaps true advancement isn't about consuming more, but thriving with less. Or maybe, as some theorists suggest, the absence of visible Dyson Spheres in the cosmos is a silent warning. Civilizations that overreach inevitably crumble. So could we build one? Technically, maybe given enough time, innovation, and luck. But the real question isn't can we, it's should we. The answer will define not just our engineering prowess, but what kind of species we choose to become. Long before astronomers seriously considered Dyson Spheres as cosmic engineering projects, science fiction writers were already dreaming them into existence, sometimes with startling accuracy. Larry Niven's 1970 novel Ringworld gave us one of the most iconic fictional megastructures, a massive ribbon-like ring encircling a star, complete with habitable inner surfaces and towering walls to contain its atmosphere. While not a full sphere, Niven's creation captured the spirit of Dyson's vision, an artificial world built on scales that dwarf planets. The physics, however, took creative liberties. A real ring world would lack gravitational stability, drifting into catastrophic collisions with its star without constant corrections. Niven later cheekily addressed this with fictional attitude jets, proving even genius storytellers need narrative workarounds for reality's harsh laws. Star Trek took a different approach in the Next Generation episode Relics, where the crew discovers a decaying Dyson Sphere so vast its interior surface could hold millions of Earths. The show's portrayal leaned into the sheer spectacle, a technological marvel so advanced even the Federation couldn't comprehend its builders. But scientifically, the structure's rigid shell ignored the gravitational and thermal stresses that make solid spheres implausible. Still, the episode nailed one key detail: the sphere's abandoned state. If such megastructures exist, they might be relics of civilizations long gone, their creators vanished but their astronomical footprints lingering. Video games have run wild with the concept too. The Halo series reimagined Dyson Spheres as weapons, massive ring worlds built by an ancient race to exterminate all life. While far from scientific, these fictional rings tapped into a deeper truth. Any civilization capable of stellar engineering would wield power bordering on godhood. Meanwhile, Dyson Sphere program, a simulation game, lets players build their own swarms, balancing energy collection with orbital mechanics in a surprisingly accurate reflection of real-world challenges. What's fascinating isn't just how fiction interprets Dyson Spheres, it's how often these portrayals circle back to real scientific questions. Niven's Ringworld sparked academic papers analyzing its stability. Star Trek's derelict sphere mirrors serious discussions about detecting dead civilizations through their megastructures. Even Halo's apocalyptic rings echo existential debates. Could stellar engineering be a precursor to self-destruction? The gap between fiction and reality reveals as much about us as the science. We imagine Dyson Spheres as utopian paradises, terrifying weapons, or abandoned tombs projecting our hopes and fears onto the cosmos. But the most compelling portrayals share one thread. They recognize that building around a star isn't just engineering. It's a statement, a declaration that intelligence can reshape the universe itself. Whether those blueprints come from physicists or novelists, the message is the same. The stars aren't just points of light, they're fuel, clay, and maybe one day home. Dyson Spheres may dominate discussions about cosmic megastructures, but they're just the beginning of what advanced civilizations might build. Imagine a computer so vast it uses entire stars for processing power, a Matryoshka brain. This nested megastructure takes the Dyson concept to another level, wrapping a star in concentric layers of energy-harvesting satellites, each radiating waste heat to power the next. The inner layers run at star-forged temperatures, while outer ones hum at cooler, more manageable energies. Together, they form a computational behemoth capable of running simulations on scales we can't fathom, perhaps even emulating entire universes. The purpose: for a civilization that's conquered physics, the next frontier might be knowledge, solving entropy, probing higher dimensions, or simulating alternate realities. But the challenges are staggering. Even with self-repairing nanomaterials, the heat dissipation alone would require engineering far beyond our grasp. And yet, if built, a Matryoshka brain wouldn't just compute, it would glow across the galaxy, its thermal signature a beacon of artificiality. Then there's the Alderson disk, a structure so bizarre it redefines habitable space. Picture a giant, flat ring with the sun at its center, its inner edge close enough for warmth, its outer rim stretching beyond Pluto's orbit. The disk's surface would have gravity perpendicular to its plane, meaning you could walk on both sides with the sun forever fixed at noon overhead. The habitable band would be a ribbon millions of kilometers wide, offering living space trillions of times greater than Earth's, but the physics brutal. The disk would need unimaginable tensile strength to avoid collapsing into the star, and stabilizing it would require gravitational anchors dwarfing planets. Some theories suggest artificial gravity generators or even dark matter manipulation technologies so advanced they border on magic. For species thinking even bigger, there's the Astrobiology thruster, a stellar engine that turns an entire star into a spaceship. By building a colossal mirrored parabola near a sun, radiation pressure could slowly push the star and its orbiting planets across the galaxy over millions of years. It's the ultimate generational arc. Instead of fleeing a dying star, you take it with you. The mirror wouldn't even need to be solid. A dense swarm of reflectors could achieve the same effect. While the acceleration would be glacial, the payoff is a universe where civilizations migrate between galaxies without abandoning their home systems. Each of these megastructures solves a different existential puzzle. Matryoshka brains transcend energy needs for pure computation. Alderson disks maximize living space without requiring faster-than-light travel. Astrobiology thrusters turn stars into lifeboats, but they all share one haunting implication. If they're possible, why haven't we found any? The silence of the cosmos grows louder with every hypothetical blueprint we devise. Either we're missing something fundamental about the nature of intelligence, or the universe hides architects whose works we've yet to recognize. Until then, these structures remain both taunts and inspirations, proof that even our wildest ideas might be someone else's ancient history. The universe might not just be silent, it could be hiding. That's the chilling premise of the dark forest hypothesis, a theory that paints the cosmos not as a bustling hub of alien civilizations, but as a shadowy wilderness where every species stays quiet to survive. Think of it like this: in a forest teeming with predators, the safest strategy isn't to announce your presence, it's to stay perfectly still, camouflaged and silent. Now apply that to the scale of galaxies. If hostile civilizations lurk among the stars, broadcasting your location could be suicide, and that's where Dyson Spheres take on a terrifying new role. Rather than beacons of advanced engineering, these megastructures might serve as cosmic cloaking devices. A perfectly constructed Dyson Sphere wouldn't just harvest energy, it could mask a civilization's heat signature, rerouting waste radiation in controlled directions instead of leaking it into space. Imagine wrapping your star in a shroud so precise, it looks like a cold, dead void to distant observers. No radio signals, no infrared excess, just the illusion of emptiness. In a dark forest universe, that's not just efficiency, it's survival. But here's the twist: even the most careful engineering might leave traces. A Dyson swarm, for instance, could cast uneven shadows as its components drift, creating flickers that defy natural explanations. And if every civilization is hiding, who built the first Dyson Spheres we do detect? Are they the reckless ones, the doomed outliers who failed to stay hidden? Or something far stranger, like ancient ruins, the skeletal remains of civilizations that thought they were safe? The dark forest hypothesis forces us to reconsider our search for alien megastructures. What if the reason we haven't found Dyson Spheres isn't because they're rare, but because the successful ones are invisible? It's a paradox. The very act of seeking them could reveal our position in the cosmic wilderness. And that raises an unsettling question. In a universe where the winners stay silent, is curiosity a luxury or a death sentence? While Dyson Spheres capture our imagination as the ultimate energy solution, they might not be the only game in town for civilizations far more advanced than ours. Consider black holes, not as terrifying cosmic destroyers, but as unimaginably efficient power plants. A rotating black hole, fed by a steady stream of matter, could convert up to 40% of that mass into usable energy through a process called the Penrose effect. That's orders of magnitude more efficient than nuclear fusion. Even more intriguing, a tiny artificial black hole, just the mass of a mountain, could emit Hawking radiation, glowing like a star while weighing almost nothing. The catch: creating or containing one would require mastery over gravitational forces we barely understand. Then there's antimatter, the ultimate energy-dense fuel. 1 gram of antimatter annihilating with regular matter releases the energy of a 20-kiloton nuclear bomb, enough to power a city for days. An advanced civilization might harvest antimatter from natural sources, like the magnetospheres of gas giants where cosmic rays produce trace amounts, or manufacture it in orbital factories. But scaling this to meet stellar-level demands is daunting. Current antimatter production is measured in nanograms per year at costs that make platinum look cheap. Even with breakthroughs containing vast quantities without catastrophic accidents, would require force fields or magnetic traps beyond our wildest engineering dreams. Zero-point energy sits at the fringes of theoretical physics, proposing that empty space itself vibrates with infinite energy. If harnessed, even a fraction could power civilizations indefinitely. Some models suggest manipulating quantum fluctuations to extract energy, though mainstream physics warns this might violate thermodynamic laws, the real barrier. We're still decoding quantum mechanics rulebook. For a species that's cracked it, zero-point energy could render Dyson Spheres obsolete. Imagine reactors smaller than a toaster powering entire worlds. So why build a Dyson Sphere if these alternatives exist? Each has trade-offs. Black holes offer insane efficiency but demand gravity control bordering on magic. Antimatter packs a punch but scales poorly. Zero-point energy remains speculative. Dyson Spheres, by contrast, are built with known physics just on insane scales. They're the brute force solution, no breakthroughs required, just time and resources. That makes them a likely stepping stone, even if not the end game. The real answer might be all of the above. A civilization mastering multiple energy sources could use Dyson swarms for baseline power, antimatter for starship fuel, and black holes for heavy lifting, a diversified cosmic portfolio. The deeper question isn't just about efficiency, it's about philosophy. A species that mines black holes might value control over nature's extremes, while zero-point harvesters could prioritize harmony with quantum fields. Their energy choices would reflect their worldview as much as their tech, and that's the silent clue in our search, not just what powers them, but what their power says about who they are. Until we find hard evidence, the debate rages, but one thing's certain. If other civilizations are out there, they aren't just living among the stars. They're rewriting the rules of energy itself. Building a Dyson Sphere isn't just an engineering challenge, it's a moral minefield. Imagine standing on Mercury, watching as autonomous machines strip the planet layer by layer, converting its iron core into solar collectors. This isn't just mining, it's planetary demolition. Does intelligence grant us the right to dismantle worlds, even barren ones? On Earth, we debate the ethics of strip mining mountaintops. But scaling that up to entire planets introduces questions we've never had to confront. Would Mercury's destruction erase potential scientific discoveries locked in its geology? Could its absence destabilize the solar system's delicate gravitational balance? And if life, even microbial, existed there undiscovered, would we become cosmic exterminators in our pursuit of power? The philosophical weight of playing solar system architect is staggering. Then there's the darker question: would constructing a Dyson Sphere make us a target? The dark forest hypothesis suggests advanced civilizations might view energy-hungry species as existential threats. A star suddenly dimming under artificial constraints could be seen as aggressive expansion, like lighting a bonfire in that metaphorical forest. History shows how resource-hungry empires provoke conflict. Would the same play out on a galactic scale? Even if no hostile aliens exist, the act of building might attract attention we can't handle. It's the interstellar version of shouting in a room you didn't realize was full of predators. But perhaps the most insidious risk isn't external, it's internal. A civilization that masters stellar engineering might stagnate under its own success. With near-infinite energy, societies could turn inward, focusing on virtual realities or hedonistic pursuits rather than exploration. the drive to push boundaries could atrophy when all material needs are effortlessly met. Human history brims with examples from the isolation of Ming Dynasty China to the technological plateau of the late Roman Empire where abundance bred complacency. Would a Dyson sphere become our gilded cage, trapping us in comfort while the universe's wonders pass us by? These dilemmas reveal a paradox at the heart of progress. To survive long-term, civilizations may need to harness stars, but in doing so, they risk losing the very curiosity and restraint that got them there. The ethics of Dyson spheres force us to ask not just what we can build, but what we should and whether some lines once crossed can never be uncrossed. The answers might determine whether we flourish among the stars or become another cautionary tale whispered in the cosmic dark. Detecting a Dyson sphere isn't as simple as pointing a telescope at the sky and looking for a giant disco ball around a star. The real challenge lies in distinguishing artificial megastructures from natural cosmic oddities, and that's where mathematics becomes our most powerful tool. Scientists start by modeling how these hypothetical constructs would interact with starlight. A Dyson swarm, for instance, wouldn't block a star's light uniformly. Instead, its countless orbiting components would create complex, irregular dimming patterns as they drift in and out of alignment. These patterns would look nothing like the smooth, rhythmic dips caused by planets, more like a flickering candle in a drafty room. To spot these anomalies, astronomers rely on algorithms trained to recognize unnatural signatures. One approach uses machine learning to sift through light curves, graphs of a star's brightness over time, flagging anything that deviates from known astrophysical phenomena. The algorithms aren't just looking for dimming, they're hunting for specific statistical quirks. Natural dust clouds dim starlight evenly across all wavelengths, but a partially built Dyson swarm might block blue light more than red, leaving a spectral fingerprint. Other models simulate how waste heat would radiate from megastructures, predicting the exact infrared glow that would betray their presence. These simulations aren't guesswork. They're grounded in thermodynamics, orbital mechanics, and materials science, creating a library of possible artificial signatures to compare against real telescope data. The most promising searches combine multiple detection methods. Imagine a star that's unusually dim in visible light but glowing in infrared, with erratic brightness fluctuations that no natural process can explain. Cross-referencing these traits drastically reduces false positives. A single oddity might be a quirk of nature, but three intersecting anomalies start to smell like engineering. Projects like GHAT and the Breakthrough Listen initiative use this multi-pronged approach, scanning millions of stars in datasets from telescopes like Kepler and WISE. They're not just looking for complete Dyson spheres. Even partial swarms or failed constructions could leave detectable traces, like finding the scaffolding of an unfinished skyscraper. Yet the biggest hurdle isn't just finding anomalies, it's ruling out every possible natural explanation. Take Tabby's star again. Its bizarre dimming initially matched some Dyson swarm models, but further study revealed dust clouds could mimic the effect. To avoid dead ends, researchers run exhaustive simulations of alternative scenarios colliding planets, rogue comet swarms, even exotic stellar physics. Only when all natural models fail does the artificial hypothesis gain traction. This skepticism isn't just caution, it's the scientific method in action. Extraordinary claims demand extraordinary evidence, and the math must be airtight before we whisper the word alien. What's astonishing is how these models keep evolving. Early Dyson Sphere searches focused on simple infrared excesses, but newer algorithms account for advanced civilizations that might minimize waste heat or use cloaking techniques. Some teams even simulate Dyson rings, megastructures built around black holes, whose intense gravity would warp light in unique, detectable ways. The math stretches our imagination, probing not just what's probable, but what's physically possible. And that's the beauty of this hunt. Even if we never find a Dyson sphere, the search itself pushes astronomy to new frontiers, teaching us to see the universe not just as it is, but as it might be shaped by hands far wiser than our own. Breakthrough Starshot isn't just another space mission, it's a radical reimagining of how we explore the cosmos. Picture this: thousands of tiny probes, each no larger than a postage stamp, equipped with microscopic cameras and sensors, propelled toward neighboring stars by powerful Earth-based lasers. These nanocraft would travel at a fifth the speed of light, reaching Alpha Centauri in just 20 years instead of millennia. It sounds like science fiction, but the physics checks out, and the project, backed by luminaries like Stephen Hawking and funded by billionaire Yuri Milner, is already in early development. Now, here's where it gets fascinating. While Starshot's primary goal is to study exoplanets, these probes could become our best hope for spotting something even more extraordinary: a Dyson Sphere up close. Think about the implications. Traditional telescopes, even mega observatories like the James Webb, can only infer the existence of megastructures through indirect clues, dips in starlight, infrared anomalies. But a Starshot probe flying through a star system could capture direct evidence. Imagine one of these tiny craft hurtling past a strange, geometric swarm of solar collectors, their angular shadows stark against the star's glow. Or detecting heat patterns that don't match any natural astrophysical process. Unlike distant observations which leave room for debate, close-up data would be unambiguous. Either you're looking at a megastructure or you're rewriting our understanding of cosmic phenomena. Of course, the challenges are staggering. Targeting a potential Dyson Sphere requires knowing where to look, and right now we're guessing. Even with anomalies like Tabby's star, the odds of a probe arriving at the right place at the right time are astronomically low. Then there's the issue of communication. A Starshot probe traveling at relativistic speeds can't slow down to orbit and study its target. It would have milliseconds to capture and transmit data before speeding irrevocably into the void. Every image, every sensor reading would need to be flawlessly automated and blasted back to Earth across light years, a whisper of data in a cosmic storm. But let's dream bigger. What if future iterations of Starshot could decelerate? Advanced versions might deploy miniature solar sails or magnetic brakes to enter orbit around a suspect star, becoming long-term observers. Or better yet, what if we discover a Dyson Sphere close enough, say, within 10 light years, that we could aim a second-generation probe with precision? Suddenly, the hunt becomes a dialogue, not just staring at distant stars, but sending scouts to knock on their celestial doors. The real triumph of Starshot isn't just the technology, it's the shift in perspective. For centuries, we've been passive observers of the cosmos, limited by the tyranny of distance and light speed delays. Projects like this flip the script, treating interstellar space not as an impassable gulf, but as a frontier within reach. And while the first probes may be simple, their successors could carry spectrometers to analyze atmospheric traces of industrial pollution, or neutrino detectors to spot artificial fusion reactors. The tools to find alien engineers might not be giant telescopes, but fleets of featherweight explorers, each a silent envoy whispering back the universe's secrets. Critics argue that Starshot is a long shot, and they're right, but so was the idea of landing on the moon before the 20th century. The project embodies a truth that defines all great exploration: you don't wait for certainty. You launch into the unknown, because that's where the answers and the next questions are waiting. And if even one probe ever glimpses the unmistakable silhouette of a megastructure against the stars, it won't just rewrite textbooks. It'll redefine humanity's place in the universe. The sheer scale of energy harnessed by a Dyson Sphere doesn't just power cities, it unlocks the stars. Imagine directing even a fraction of a star's output toward propulsion, and suddenly, interstellar travel shifts from daunting to inevitable, the first and most straightforward method. Generation ships vast arcs carrying entire populations across centuries-long voyages. With a Dyson swarm's energy, these wouldn't be the cramped, fragile vessels of sci-fi. Picture continent-sized habitats propelled by colossal ion drives or nuclear pulse engines, their interiors lit by artificial suns, their trajectories adjusted by megawatt-range lasers firing from the home system. Such ships could sustain ecosystems, cultures, and even evolving generations, all while recycling every atom of waste into food, air, and fuel. The challenge has never been feasibility, it's been energy. And with a star's worth of power, that barrier evaporates. But why stop at slow boats? A Dyson Sphere could theoretically fuel something far more audacious: antimatter propulsion. Right now, producing even a gram of antimatter takes years and consumes more energy than it releases. But a civilization tapping its star could manufacture it on an industrial scale. Antimatter engines could accelerate ships to relativistic speeds, shortening a trip to Alpha Centauri from millennia to decades. The numbers are staggering. 1 kilogram of antimatter annihilating with regular matter releases the energy of 43 megatons of TNT. Now scale that up. A Dyson-powered antimatter factory could produce tons annually, enabling fleets of starships to crisscross the galaxy like commuter trains. Then there's the Holy Grail, warp drives. While still theoretical, concepts like the Alcubierre drive suggest that bending spacetime itself might be possible with enough energy, specifically negative energy. A Dyson Sphere could provide the power to create and sustain such exotic physics. Picture a network of energy beaming stations across the solar system, funneling stellar output into warp coils that compress spacetime ahead of a ship and expand it behind. The vessel wouldn't move through space. Space would move around it, sidestepping light speed limits. The energy demands, absurd by our standards, equivalent to converting Jupiter's mass into pure energy. But for a Type 2 civilization, that's just another day at the cosmic power plant. But here's the catch: even with limitless energy, interstellar travel isn't just about propulsion. Navigation becomes a nightmare at relativistic speeds. A pebble hitting a ship at near light speed carries the force of a nuclear blast. Shielding would require force fields or plasma bubbles powered by, you guessed it, even more energy. And then there's time dilation. A crew traveling at 90% light speed would age slower than those left behind, returning to a home system centuries older. Would societies splinter over these time gaps? Would starfarers become estranged from their own species? Perhaps the most intriguing possibility isn't physical travel at all. With Dyson-level energy, a civilization might opt for digital migration, uploading consciousness into light-speed data streams beamed to receiver stations across the galaxy. No ships, no risk, just pure information riding laser highways through the void. It's a haunting vision, exploration without explorers, where the only vessels are pulses of light carrying the essence of a species. Whether through generation ships, antimatter rockets, or warp bubbles, one truth emerges: energy is the key to the cosmos. A Dyson Sphere isn't just a power source, it's a launch pad, turning a single star system into a hub for galactic civilization. And that raises a tantalizing thought. If other species have already built them, the Milky Way might not be silent. It could be bustling with traffic, invisible only because we're still learning to see the roads. Earth's biosphere is a marvel of self-regulation, a delicate dance of organisms, oceans, and atmosphere that maintains conditions perfect for life. From bacteria adjusting oxygen levels to forests regulating rainfall, our planet functions like a living, breathing organism. This idea, known as the Gaia hypothesis, suggests Earth isn't just a rock hosting life. It's a vast, interconnected life support system fine-tuned over billions of years. Now scale that up to a civilization capable of engineering on a stellar level. Could a Dyson Sphere be the ultimate extension of this principle, not just sustaining life, but actively crafting a habitat on the scale of a solar system? Think of it this way: just as Earth's biosphere recycles carbon, water, and nutrients to maintain equilibrium, a Dyson swarm would balance energy capture, waste heat dissipation, and orbital stability to support its builders. The parallels are striking. Both systems involve feedback loops. Earth's ice albedo effect has its counterpart in the swarm's thermal management. Both demand precision. A single runaway greenhouse gas can doom a planet, just as a miscalculated orbital trajectory could collapse a megastructure. And both are acts of stewardship. If Gaia represents nature's unintentional genius for sustaining life, a Dyson sphere might be intelligence's deliberate answer to the same challenge, survival at scale. But there's a crucial difference. Earth's balance emerged through trial and error, a slow grind of evolution and extinction. A Dyson sphere would be a conscious choice, a declaration that a species has taken control of its cosmic environment. That raises profound questions. Is dismantling planets to build stellar engines an act of responsibility or hubris? Does stewardship mean preserving worlds as they are, or reshaping them to guarantee a future? Indigenous cultures often see themselves as part of Earth's web, not its masters. Would a Dyson sphere civilization retain that humility, or would it slip into the role of cosmic landlord, treating stars as property? The answer might lie in intent. A Dyson sphere built purely for unchecked energy consumption could be a tombstone, a sign of a civilization that prioritized growth over harmony. But one designed with closed-loop systems, where every joule of waste heat is recycled and every mined asteroid replanted with habitats, might echo Gaia's wisdom. Imagine megastructures that mimic ecosystems, solar collectors, photosynthesizing starlight, orbital habitats with artificial atmospheres as balanced as Earth's, even engineered species of robots repairing and adapting the swarm like microbial decomposers. This wouldn't just be engineering, it'd be biomimicry on a galactic scale. The Gaia hypothesis forces us to confront a humbling truth: life and environment are inseparable. A Dyson sphere built with that insight wouldn't just power a civilization, it'd embody one, reflecting the same delicate balance that keeps our planet alive. The universe might be full of such creations, not as cold megamachines, but as cosmic extensions of the same impulse that spins spiderwebs and builds beehives, the urge to craft a home. And that's the ultimate question: are we destined to be tenants of the universe or its gardeners? The difference could determine whether our fingerprints on the stars are scars or masterpieces. Imagine a civilization where energy is as abundant as the air we breathe, where the concept of scarcity doesn't apply to power, only to imagination. That's the promise of a human-built Dyson sphere, a society no longer shackled by the need to ration resources, where every individual and every machine could operate at the peak of possibility. But with such radical abundance, humanity itself would undergo transformations we can barely fathom. Would we remain the same species that once huddled around campfires, or would we evolve into something entirely new? First, consider the basics: daily life in a Dyson-powered society. Energy poverty vanishes overnight. Cities could float in the sky, buoyed by anti-gravity tech or sheer propulsion, their streets lit by artificial suns. Climate change reverses as carbon capture becomes trivial when energy costs nothing. Deserts bloom with vertical farms, oceans teem with bioengineered reefs. Even space travel becomes routine, with orbital elevators or lunar shuttles as commonplace as subway trains. The line between home and the cosmos blurs because with a star's energy at our disposal, why limit yourself to Earth? Yet abundance alone doesn't guarantee utopia. History shows that when resources surge, so do ambitions and conflicts. Would we use this power to uplift everyone equally, or would old inequalities simply scale to galactic proportions? Picture corporate empires wielding Dyson-powered AIs, their influence stretching across star systems while fringe colonies fight for scraps, or worse, a society so addicted to growth that it cannibalizes neighboring stars, sparking interstellar resource wars. Energy might be infinite, but matter isn't, and the temptation to dominate could fester even in paradise. Then there's the question of identity. With limitless energy, we could transcend biology itself. Minds might upload into quantum networks, living as digital entities in matryoshka brains. Bodies could be rebuilt atom by atom, ageless and adaptable, swapping forms like outfits. Would we still call such beings human, or would they be the next step in evolution? And what happens to art, love, or curiosity when every desire is instantly fulfilled? The Renaissance flourished because scarcity bred creativity. Would a post-scarcity society still produce Shakespeares and Einsteins, or would we drown in an ocean of comfort? Perhaps the most profound shift wouldn't be technological but philosophical. A species that builds Dyson Spheres isn't just mastering energy, it's declaring itself steward of the cosmos. Every action carries stellar consequences. Redirecting a star's output could destabilize local space. Dismantling planets erases cosmic history. With such power comes an ethical weight unlike anything we've faced. Do we become gardeners of the galaxy, nurturing life wherever we find it, or conquerors, reshaping reality to our whims? The answer might define not just our future, but the legacy of intelligence itself. One thing is certain, humanity wouldn't be the end point of this journey, we'd be the bridge. The civilizations that thrive among the stars won't look back at us as ancestors, but as pioneers, the ones who dared to reach beyond their cradle, who turned sunlight into a springboard for the universe. Whether that future is glorious or tragic depends on choices we're making right now, because the first step toward building a Dyson Sphere isn't engineering. It's deciding what kind of civilization deserves to harness a star. The universe is full of mysteries that defy easy explanation, cosmic anomalies that linger in scientific debates, teasing the line between natural wonder and potential alien engineering. Take fast radio bursts, those bizarre millisecond-long blasts of energy detected from deep space. Some originate billions of light years away, packing the power of hundreds of millions of suns before vanishing without a trace. Most are likely caused by cataclysms like colliding neutron stars or evaporating black holes, but a handful repeat, flashing at irregular intervals with no obvious source. Could these be something else entirely? In 2019, astronomers observed a fast radio burst from a galaxy 500 million light-years away with a pattern eerily reminiscent of a lighthouse beacon, a steady, repeating cycle. While the odds remain slim, it's not impossible to imagine an advanced civilization using directed energy for communication or propulsion. A Dyson-powered society might harness such bursts to push light sails across galaxies, turning entire stars into engines for interstellar travel. Then there's Oumuamua, the first known interstellar visitor to our solar system. Its elongated shape, unusual trajectory, and sudden acceleration defied all expectations. Natural explanations range from a shard of a shattered planet to a hydrogen iceberg venting gas. But Harvard astronomer Avi Loeb famously suggested an alternative. Could it be artificial? Its tumbling motion and reflectivity matched no known asteroid, while its acceleration without visible debris resembled a light sail catching starlight, a relic of alien technology adrift between stars. Skeptics rightly point out that extraordinary claims require extraordinary evidence, and Oumuamua's mysteries could still have mundane roots. Yet its very strangeness forces a question. If we found a derelict Dyson swarm component or a broken solar sail, would we even recognize it? Our solar system could already be littered with alien artifacts, disguised as space rocks or overlooked as noise. Deeper still is the case of KIC 9462945, a star that dimmed so dramatically, astronomers initially had no framework to explain it. Unlike Tabby's star's erratic dips, this one plunged by 80% for weeks, as if something vast and opaque drifted across it, the best natural guess. A colossal ringed planet, eclipsing its star in a way never seen before. but the numbers strain credulity. The object would need rings stretching millions of kilometers, dwarfing even Saturn's. Compare that to a hypothetical megastructure under construction, a partially completed Dyson ring or a failed swarm cluster, and the anomaly suddenly feels less like an outlier and more like a clue. These phenomena share a tantalizing thread. They resist easy classification. Nature rarely operates in straight lines or perfect geometries, yet some of these events flirt with patterns that feel deliberate. That doesn't mean they're proof of aliens, but they do highlight how little we truly understand about the cosmos. Every unexplained flicker or rogue object could be a dead end, or it could be the first breadcrumb in a trail leading to intelligence beyond Earth. The search for Dyson spheres isn't just about spotting megastructures, it's about redefining what we consider possible. If another civilization has mastered stellar engineering, their signatures might not be sleek spaceships or radio greetings. They could be the subtle, scattered remnants of ambition, mislabeled as cosmic oddities until someone looks closer. The universe isn't obligated to announce its engineers. Sometimes the most profound discoveries begin with a simple question: what if we've been misreading the clues all along? For all their grandeur, Dyson spheres come with glaring blind spots, starting with the assumption that advanced civilizations would inevitably follow our own technological trajectory. Human history shows innovation rarely takes straight paths. Societies leapfrog stages rather than follow predictable progressions. Medieval Europeans couldn't have imagined skipping steam power for solar panels, yet some cultures might. Why assume aliens would prioritize massive stellar engineering when they might discover compact energy sources we haven't dreamed of? Our obsession with Dyson spheres could say more about humanity's current bottlenecks than universal rules for intelligence. Then there's the brute force impracticality. Dismantling planets requires moving incomprehensible amounts of matter against gravity, a process so energy-intensive it might cancel out the gains. Even with self-replicating robots, construction could take millennia, leaving swarms vulnerable to asteroid impacts or civilizational collapse long before completion. The late physicist Stephen Hawking once noted that the most advanced civilizations might avoid megastructures altogether, opting instead for digital existence in optimized substrates requiring negligible energy. A single Jupiter-sized supercomputer running at near absolute zero could theoretically outperform a Dyson-powered Matryoshka brain while consuming a fraction of the resources. Occam's razor slices through many D-sphere hypotheses. When astronomers spot a strange infrared signature or erratic starlight, the simplest explanation is usually cosmic, not artificial. Dust clouds, colliding planets, or rare stellar phenomena account for most anomalies without invoking alien engineers. The burden of proof for extraterrestrial intelligence is justifiably high. Extraordinary claims shouldn't lean on cosmic scale, maybe S. Even Tabby star's bizarre dimming, once hailed as a potential Dyson swarm, was eventually attributed to clouds of micron-scale dust, a mundane answer hiding in plain sight. Cultural bias also warps the search. Humanity's industrial age mentality frames energy harvesting as the pinnacle of advancement. But what if post-scarcity civilizations value equilibrium over expansion? Indigenous Earth cultures often prioritize harmony with nature over domination. Alien societies might view dismantling stars as barbaric. The very concept of a Dyson sphere could be a projection of our own unsustainable growth models onto the cosmos. Perhaps the sharpest criticism is temporal. Stars have burned for billions of years. Intelligent life might flicker briefly in comparison. The odds that we're observing another civilization's engineering project during their narrow construction window are vanishingly small. What we interpret as D-sphere candidates might just be cosmic debris, the ruins of endeavors long abandoned, or natural processes we've yet to classify. Skepticism isn't cynicism, it's rigor. The hunt for Dyson spheres pushes science to ask better questions, even if the answers defy our fantasies. Every dead end teaches us more about stellar physics, and every anomaly ruled out sharpens our tools for the ones that remain. The universe doesn't owe us aliens, but the search itself expands what we know is possible. And that's the paradox. The more we learn, the stranger and more wonderful reality becomes. Finding a Dyson sphere wouldn't just rewrite astronomy textbooks, it would shatter humanity's cosmic self-image in ways we're scarcely prepared to confront. For centuries, we've measured intelligence by human standards, tool use, language, the ability to reshape environments. But a megastructure enveloping a star would render those metrics laughably quaint. Suddenly, intelligence wouldn't mean building cities or sending probes to Mars. It would mean rearranging solar systems like furniture, treating stars as raw material. The psychological whiplash could dwarf even the Copernican revolution. When Galileo proved Earth wasn't the universe's center, it triggered existential crises. Discovering that we're not even the most competent builders in the galaxy might humble us to the point of paralysis or ignite an unprecedented surge of ambition. Yet the deeper revelation wouldn't be about alien capabilities, it'd be about time. A functioning Dyson sphere implies a civilization that survived its own technological adolescence, avoiding self-destruction long enough to achieve stellar engineering. That longevity alone carries a haunting message. Intelligence can endure. In a universe where species might routinely annihilate themselves with nuclear war, climate collapse, or runaway AI, the builders of such a structure would be the ultimate outliers, proof that the great filter, the hypothetical barrier preventing life from advancing, isn't insurmountable. Their existence would offer both comfort and dread. Comfort that someone made it through, dread that we might not. The social ramifications on Earth could split humanity along ideological fault lines. Some would see the discovery as a rallying cry, evidence that cooperation on a planetary scale is possible, that our petty divisions are obstacles to cosmic greatness. Movements might emerge to accelerate space industrialization, viewing the Dyson sphere as a blueprint rather than a curiosity. But others could recoil in terror, interpreting the megastructure as a threat. Conspiracy theories would flourish. Are its builders watching us? Are we next? Political factions might clash over whether to hide from such advanced beings or attempt contact, replaying the colonial anxieties buried in our collective memory. Religions would face their own reckonings. A Dyson sphere challenges anthropocentrism more profoundly than any exoplanet discovery. If gods made humans in their image, what does it mean when other beings reshape stars? Some faiths might adapt, framing the builders as divine agents or kindred spirits in creation. Others could fracture, their cosmologies rendered provincial by the scale of alien achievement. Historically, contact between advanced and indigenous cultures rarely ended well for the latter. Would spiritual systems collapse under the weight of this new cosmic hierarchy? Then there's the question of imitation. If we confirm Dyson spheres exist, should we build our own? The ethical debates would rage. Is stellar engineering an evolutionary imperative or cosmic vandalism? Proponents might argue that harnessing the sun is our destiny, the only way to secure humanity's long-term survival. Critics could counter that chasing alien blueprints risks repeating their mistakes. What if Dyson spheres are tombstones, not triumphs? The very act of choosing would redefine what it means to be human. Are we explorers, conquerors, or something else entirely? Perhaps the most unsettling implication is solitude's end. A universe with Dyson spheres is one where intelligence isn't just possible, it's prolific. But if such civilizations are common, why haven't they contacted us? The silence beyond their megastructures might suggest indifference or something darker. Alternatively, their existence could mean we're latecomers to a galactic community that operates on timescales we can't perceive. Either way, the discovery would force us to stare into the abyss of cosmic sociology. grappling with questions we've only ever posed in fiction. What do civilizations talk about when they've mastered stars? What do they value when energy is infinite? And where in that grand spectrum do we fit? The irony is palpable. A Dyson Sphere's physical footprint would be unmistakable, blazing across telescopes. But its true impact would be internal, a mirror held up to humanity's aspirations, fears, and fragile self-concept. Confronting such a discovery wouldn't just teach us about aliens. It would teach us about ourselves, whether we're ready to grow up as a species or whether we'll remain cosmic children, forever gazing at the stars but never reaching them. Dyson Spheres captivate us not because they're plausible, but because they're audacious. They represent the furthest edges of human imagination, structures so vast they bend the laws of physics and redefine what a civilization can achieve. From Freeman Dyson's two-page thought experiment to today's high-tech hunts for infrared anomalies, the pursuit of these megastructures has reshaped how we view the cosmos. They're more than hypothetical energy solutions. They're mirrors reflecting our deepest hopes and fears, the hope that intelligence can endure long enough to touch the stars. The fear that we might be alone, or worse, that we'll destroy ourselves before we ever get the chance. This search has already transformed astronomy. Projects like GHT and Breakthrough Listen have turned starlight into a cosmic detective story, sifting through data for the faintest hints of alien engineers. Every oddity, Tabby's star's erratic dimming, Oumuamua's unnatural acceleration reminds us that the universe is stranger than fiction. Even when natural explanations prevail, they push science forward, sharpening our tools for the next mystery. The absence of proof isn't failure, it's motivation. If Dyson Spheres are out there, they're hiding in plain sight, waiting for us to look harder. What makes this quest timeless isn't just the science, it's the questions it forces us to confront. Are we destined to harness stars, or is our future something we can't yet envision? Would a civilization capable of such engineering share our values, or would they be as alien to us as we are to ants? The silence of the cosmos might feel oppressive, but it's also an invitation. Every unanswered question is a blank page, urging us to keep exploring, testing, and dreaming. So stay curious. The next breakthrough might come from a backyard astronomer spotting an anomaly, a lab uncovering new physics, or a probe sending back images of something impossible. The universe doesn't owe us answers, but it does offer clues hidden in starlight, encoded in mathematics, waiting for those stubborn enough to look. Whether Dyson Spheres exist or not, the search itself has already changed us. It's proof that humanity, for all our flaws, remains a species that stares at the night sky and dares to ask, what if? And that's a legacy worth building.